Hello friends, we are going to study about shafts. And shafts in engineering, they are used for transmitting power. We are going to analyze the different formulas for a hollow shaft and a solid shaft. The strength or the strength of the shaft, which is the power transmitted by the shaft, so it can be approved. We are going to consider a shaft which is cylindrical. We are going to take a section and we take an element of thickness dr and the radius of the whole shaft being r. We are going to prove the strength of the shaft, which is going to be, we are going to get first the area of the element, of the shaded element, which will be equal to area of a circle, pi r squared, pi r. Now, when you observe the radius, we are going to get the radius of this, we are going to get from the center or up to this edge. So it means that from this from this center up to the edge of the element will be r plus dr, which is the thickness of the shaft, squared minus pi r, which is this, which is the area of this. So when we try to open this bracket, it will be pi into r squared plus 2r dr plus dr squared. This is the bracket which I've opened, r plus dr squared. Then we are going to subtract pi r. Then for small changes, you find that a small change dr in errors, this tends to 0. So we are going to have dA is equal to r squared plus 2r dr plus dr squared, pi r squared, the area of this inner part. So when you observe 2 pi r dr minus r squared, this is going to reduce with this, and I remain with 2 pi r dr. This is the area of the element. Now remember, there is a tangential force dt that we are going to be observing. Remember, we are getting the strength of the shaft, and it is measured as the power transmitted by the shaft. So we are going to take, using the relationship between in the torsional formula, T, which is the tension, maximum tension out of polar moment of inertia, is equal to G theta, which is the twist, out of L is equal to the shear stress at a distance r from the center is equal to Ts over r. This is the torsional formula which we are going to use. We know that we want to get the tangential force that is acting on the element, which is going to be, we are going to relate this part in the torsion equation, which is T, which is the tangential stress on the element over r, is equal to the tangential stress at the surface of radius r from the center. So we are going to use this formula. We make we make the tangential stress at a distance r, the subject weight, which is going to be r times tangential stress at the surface over R. Then we know that the tangential force, to get the tangential force that is acting on the element is going to be, we know the relationship between force. This will be the tangential force acting on the element is equal to the area dA times TR, the tangential stress on the element. So we substitute, we come and get our equation 1, we substitute in equation 2. For area, it is 2 pi r dr, pi r dr times tangential stress at the element, and substituting for tr, this is r tangential stress at the surface over the radius r. We find that this becomes 2 pi r squared tangential stress at the surface over r times dr. This is the tangential force acting. Now to get to the torque, remember our aim is to get this torque that is acting at the element. Torque, which will be equal to the torque, a small torque that is acting on the element, as is going to be given as the force, the tangential force that is acting on the element, Fr times the perpendicular distance from the center, which is R, the perpendicular distance to the tangential torque acting on the element. So Fr times R, this will be giving us the small torque acting on the element. Then substituting for Fr, which is the tangential force on the element, this makes this R cubed T, tangential stress at the surface dr over R is equal to dt. Now to obtain the total torque maximum acting on the whole shaft T, on the whole shaft, we are going to integrate dt. We are going to integrate dt, and on this side from 0 to R of 2 pi R cubed tangential stress at the surface out of R dr. Now integrating this, remember remember 2 pi Ts, which is the tangential stress at the surface, and 2 pi over R are constants. So integrating from here will be equal to R power 4 over 4, substituting in our limits from 0 to R, and substituting this makes our T, which is the T max at the surface of the shaft, being 2 pi R, 2 pi the tangential stress times, substituting in the limit, the upper limit, since the lower limit is 0, this makes R power 4 out of R times 4. And we can observe our R is going to reduce the power to 3. And if we continue, we find that our torque max that will be at the acting on the shaft will be equal to 2 pi the tangential stress at the surface R cubed over this 4, but the 4 can reduce with the 4 can reduce with the 2, and we'll find ourselves having pi over 2. And we can substitute for r being equal to d over 2. So it means that when since it is power 3, it is 3 here, 3, then this is going to reduce to 8. Substituting for r power 3 in the equation, this will be pi tangential stress d cubed over 16. This will be the formula for the maximum torque for the solid shaft.